Last time we took a look at section 8.5, partial fractions, and as we were looking at this, we did one example, and the key idea in doing this is to take the denominator and to factor it out, right? And put arbitrary values on top that are degree 1 less, and we didn't have very exciting denominators on this, so our degree 1 less were just constants a and b. And then multiply the fractions back together to try and figure out what a and b would have had to have been for that to actually work. And then once we've done that, we end up with simpler fractional expressions that we're actually able to integrate. That's the plan of partial fractions. So we're going to do another example. This example has a little bit more complicated of a denominator for a couple of reasons. So let's take a look then at what happens when we attempt to factor this particular denominator. Whoops. Get my black back out. Okay, so if I factor this denominator, what do I get? Don't everybody talk at once. Oh, factoring's been a while, it looks like. There's only two terms. What do they have in common? X squared. So we pull an x squared out. What's left? Okay. Are y'all still with me? Okay, good. I'm glad to hear it. 4x squared on top plus 2x minus 1. Okay, everybody good so far? Okay, now here's where the tricky thing happens. Actually, it's right here. We have a denominator of x squared, or at least we're going to have a denominator of x squared, but we're also going to have a denominator of x. So when I separate this out, I end up with one denominator of x, one denominator of x squared, and one denominator of x plus 1. So let me explain what happened to that. Basically, we're separating this into all of the possible fractions that could have existed to add together to give us the original fraction we just started with. And all of these denominators could be present and still be reconciled to have that same common denominator of x cubed plus x squared, right? So that's what we're doing. So it feels kind of funny because I've written down an x and I've written down an x squared. But anytime there's a duplicated root like that, where you've got something squared, you're going to have that happen. So like if you had, for instance, a denominator where you ended up with x plus 1 squared times x plus 2, you'd end up with one denominator that's x plus 1, one denominator that's x plus 1 squared, and one denominator that's x plus 2. You'd have all of them. Okay? So duplicated roots give you both the linear factor, the squared factor. If they were a cubed factor, you get one of those. I mean, you get all of the pieces of that. Okay, everybody good so far? Okay, now, let me erase this piece right here so I have more space. All right, so back up with what we were doing then. What we need to do is we need to write the numerators with degree 1 less. So in the first denominator, I just have x. That has a degree of 1. It's 1, so the numerator will be a constant. You're right. So I'm going to have a constant in my numerator. So it will be, I'm going to write minus a. When we duplicate the denominators, like this, x and then x squared, I know it didn't exactly duplicate, but you know what I'm saying, right? When we have that happen, we don't have to worry about the second denominator having degree 1 less. It also can be a constant. That's sufficient. Don't overcomplicate when you don't have to, and I'm just letting you know you don't have to. And then the third numerator is also going to be a constant because it's a degree 1 in the denominator. Okay, I do have an example here on part C where we're going to have something that's actually a squared in the denominator that we have to deal with differently, so you can see what it looks like for that too. But if you have that duplicated denominator business going on, you actually get to have a linear constant, or it's acting like a linear one as well, so you get a numerator that's just a constant. Do you remember what we did next last time after we got those individual numerators of a, b, now we have a, b, and c? Right, we combined the fractions back together by getting a common denominator. So our denominator on this needs to be the same denominator that we just had a minute ago, right? So this first fraction will have to be multiplied by x and x plus 1. The second fraction will have to be multiplied just by x plus 1, right? Is that green visible enough? It's a little bit bright. But, and then the third fraction will be multiplied by what? Yeah, somebody said x squared. All right, so we need to multiply multiply these and clean them up. So in the first one I have ax squared plus ax. On the second one I have bx plus b. And on the third one I have cx squared. And all of this is over x squared times x plus 1, or you can write it out as x cubed plus x squared if you'd like. Dx at the end. Okay, so what we did on the last one is we collected the different types of terms we had. We compared constant terms and linear terms because that's all we had over here, right? Everything that's highlighted in blue there was either a constant or it had a single x with the power of 1 in it. So constant or linear. On this one, we have constant, we have linear, and we have quadratic. Are y'all with me? So we're going to have to collect 3 different types of terms. One of them will be our constant terms, they're our numbers. One of them will be our x terms, that's our linear terms, and one of them will be our x squared terms. So looking at the numerator that we have over here, what are our constant pieces? Just b, it's the only one, right? So it's just b. What are our linear pieces? An ax and a bx, right? So, and they're added, so it's an a plus b, and they're times x. That's why I'm writing the x out in front of it. It's kind of like I'm factoring it out. And then what are our x squared terms? It's an ax squared and cx squared, so it's a plus c, and those are our x squared terms. We go back and we compare that to the original numerator. And the original numerator tells us what we should be getting for our linear, our constant, and our squared terms. What is our our constant, that's my first one listed, supposed to be? -1 on the constant, right? And that's actually really nice because that just solved one of the variables for us, didn't it? We know that b is -1 because of the way this particular problem worked out. What is our linear coefficient? 2. So can I use the fact that b equals -1 right here to solve for a? Yeah. So what would a be? 3, right? If I plug in -1 for b, a would have to be 3. What is our quadratic value? 4. And if I know that a is 3, what is c? 1. So this one solved really, really nicely for a, b, and c, didn't it? And you might have had a feeling looking into it at the beginning going, oh my goodness, I have 3 variables, 3 unknowns, this is going to be a mess. It's really hard to tell that on these particular problems looking at them from the front end. 3 equations does not necessarily mean that they're going to be 3 difficult equations. So coming back over to this point right here where I had done it with the a, b, and the c with the separated denominators, I can actually rewrite them with the separated denominators. The first one was a, and that's 3. So it's 3 over x. The second one is b, and b is -1. So I'll just write this as a subtraction, 1 over x squared. And then I have c, which is 1 over x plus 1. And you have the ability to integrate every piece of that. What's going to happen when you integrate the 3 over x? It's going to be a log, right? You're going to get a natural log. I'm actually going to do it here in a second. The second piece, the 1 over x squared, that's not a log, correct? Not a log. So that one would be helpful for us probably to think about as being rewritten as -x to the -2. The third one is also a log. What is it that makes the third one a log? Why is the first one and the third one a log and the second one's not? Maybe I should ask the question that way. What was it, Jaden? Yeah, it's the exponent that tells us, right? The first one and the third one have an exponent of 1 on the x, and the second one an exponent of 2, or -2 in the case, as the case may be. Okay, so the first one and the third one are logs. The second one is a power rule. So let me copy this to the next page, if I have some space. If not, I will, if I do, okay. Okay, cool. So the first one, what will its antiderivative be? 3 natural log of, somebody said it, absolute value of x. Be careful with that one, right? You wrote it down, you just didn't say it. Well, I'm good with that. I've got a negative. What about the antiderivative of x to the negative 2? Yeah, negative 1 over negative 1. We'll simplify that here in just a second. And then I've got the other piece. So what is this one? 1 over x plus 1. Natural log of absolute value of x plus 1. And then I'm going to need a plus c. Very good. 2 pieces of cleanup. This one is a very clean piece of cleanup. It's easy, right? It's plus 1 over x. The piece at the beginning and the piece at the end can be combined. And by the end, I don't mean the plus c, but the parts I underlined. They're both logs. How can I combine them? And you can combine with multiplication, but there's something we have to do before the multiplication as well. Did anybody see it? The 3. This 3 has to be moved into as an exponent before I can actually combine the logs. The property for logs only allows us to work with coefficients of 1 in front of the logs. So I need to move that coefficient of 3 as an exponent. So this is actually going to be the natural log of the absolute value of x cubed times x plus 1. And that still has the chance of being negative, so we do still need the absolute values on there. And of course the plus c at the end. Any questions on that one? Okay, so the only part on that one that makes it tricky is remembering that right here, I don't exactly follow the rule that I just said before. I should not highlight it in blue. Let me try to choose a different color. Right here, the rule is slightly different, right? We have to double the denominators. We have to use a linear factor instead of or a constant factor instead of linear factor. And that part looks and feels kind of funny. All right, so let me show you the next one. This is our last example in this section. The denominator is already actually in factored form for us, right? I mean, it's already written as something squared. And I mentioned on the previous one that when we have a squared, what it means is that we're really going to have 2 denominators. One of them that's the coefficient of 1, so x squared plus 9 to the 1 power. And then the other one that is the x squared plus 9 squared power. Okay, so we duplicate the denominator, one of them with an exponent of 1 around the whole thing, and the other one with the exponent that's the 2, that is the bigger of the 2 options as well. Now because we duplicate them, actually let me just do the first piece first. X squared plus 9, that's quadratic, right? Degree 2. So I need a numerator that's a degree 1. What is a degree 1, what's an example of a degree 1 function? Just x. But I might have coefficients involved as well, right? So the most general way of writing a linear function looks like this. You probably saw it way back in, I don't know, 7th grade. Y equal mx plus b, right? The equation of a line. We kind of like to use variables in order for some reason, so I'm using the ax plus b, which is a little bit more standard. Now, the second denominator, because it duplicates the first one, but with just a higher power, we also can ignore the fact that it's really a degree 4 polynomial. We can treat it as though it's a degree 2. So in other words, we get to ignore this exponent for the moment, just pretend like it's not there, and we recognize that this is x plus 9. I'm sorry, it should say x squared. Yes, x squared plus 9. We get to ignore the square that I circled on the outside, though, so we're going to treat it like it's a quadratic. So it means the numerator needs to be linear, and I don't want to use the a and the b that I just used, so what do you think I might let the numerator be instead? Yeah, cx plus d. So if you had a quadratic denominator, you're going to have a linear numerator. What would happen if you had a cubic denominator? Yeah. ax squared plus bx plus c. I don't think you're going to encounter one like that, but that's what you would do. It would look like the quadratic equation on top, right? Or the quadratic, general form of a quadratic on top. Okay, cool. What do we do next after we have written these arbitrary constants in our numerators? We multiply them back together. And the nice thing about this is that that second fraction already has the common denominator in it, correct? So I don't have to do anything on the second fraction. On the first fraction, I will multiply by the x squared plus 9. So my ax plus b will be multiplied by x squared plus 9. So we're going to multiply everything back together. Of course, the denominator is now x squared plus 9 squared. And we're going to FOIL out the numerator. So somebody tell me what you're going to get. No, I think you're right. Ax cubed, that's what we have, ax cubed. And then what? Plus, what did you say, Evan? Bx squared, right. 9ax, and then 9b. And then the other pieces are cx and d, right? And there's a dx here at the end that I'm kind of running out of space to write in there. Okay, very good. So we're going to collect like terms. Now notice we've got powers and so forth that start with, what's our highest? Yeah, power 3. We've got x cubed terms. We've got x squared, x, and constants. So what are our x cubed terms? A, right? Yeah, ax cubed, so it's just a. What are our x squared terms? Just b, right? Plain old b, huh? All right, cool. What are our x terms? 9a, 9b. No, I don't think there's a 9b. Let's take that one off. 9a and c, right? Okay, what are our constant terms? Yeah, there's the 9b and d. Okay, so that's all collected from our new fun expression that we have on the numerator. And now we're going to go back and compare that to what the original fractions numerator really was. What are the x cubed coefficient on the original numerator? It's 0, because there isn't an x cubed, right? Well, that's kind of friendly. I know what a is. How about the b? What is the coefficient on the linear, or on the quadratic x squared terms? It's a 1. How cool is that? I already know what b is. What about the linear terms? Right, it's going to be a total of -1, and you're right, Abby, because the a is 0. This also tells me then that c is -1. And then what about my constant terms? They're 9, right? First, the sum is 9. Since b is 1, this will mean that d is what? 0. So, man, that's just so nice. We got 1s and 0s everywhere. So I know now that a is 0, b is 1, c is -1, and d is 0. And I can come over here and I can rewrite this from the factored piece, right? A is 0, but b is 1. So the first fraction is 1 over x squared plus 9. Is that good? The second fraction has a cx plus d. Well, d is 0, and c is -1. So what do I get for this one? Yeah, I get -x, and then the denominator is the x squared plus 9 squared dx. All right. These are not logs. The antiderivatives are not, right? Why not? Because they have powers on the x's. So don't go thinking just because you got denominators, you got logs. These don't. That first fraction, x squared plus 9. Doesn't have a numerator with an x in it, so I can't do u substitution. I think the second one I can, right? The second piece is a u substitution piece. If u is equal to x squared plus 9, then du is going to give me the numerator, or pretty close. What am I going to do about that first one? It should look and feel like something you've seen before. Do you remember, Hannah? Evan, what do you think? It is an arctangent. That's exactly right. The arctangent is that you have addition between two values that appear to be squared, and one of them in particular is the variable squared. The other one could be anything constant, and then you use the square root. This one actually is pretty friendly because it's 3, right? Okay, cool. So we're going to get arctangent from the first piece. So let me do the first piece and the second piece separately. So we have x squared plus 9 dx. This one's going to be the arctangent piece. This one's minus an x over the x squared plus 9 quantity squared. This one's going to be a u substitution. Okay, so arctangent. What is it going to be? I'm going to have an arctangent. Is there a value in front of it? Is there a value inside? What do I need?
1/3 arctangent of x over 3.
That sounds right to me. That's what I have written down as well. Okay. This is 1/3 because it's 1 over the a value, and a is 3. Arctangent of the u value, which is our x, over our a value, which is our 3. All right, the second piece, what will u be? X squared plus 9, so what is du? 2x dx. I don't have a 2, so I'm going to have to divide by it, right? So I've got a negative 1/2 in front times the integral of 1 over u squared du. Still no natural logs, right? This is minus 1/2 the integral of u to the negative 2 du. What's the antiderivative of u to the negative 2? U to the negative 1 over negative 1. So this ends up being a plus 1 over 2u, and u is x squared plus 9. Okay, so I'm going to go back in here. I'm going to write all these down. Each step is supposed to be the same as the next. You can if you want. I'm not sure that it's really simpler either way, so it's kind of your choice. And at some point in here, it would be this point, I started having plus c's, right? So I have 1/3 arctangent of x over 3 plus 1 over 2 times x squared plus 9, and you can distribute that if you'd like, and then plus c.